Every single morning, for as long as humanity has existed, it has happened. A silent, gradual, and utterly reliable miracle. The world is bathed in light. Our planet, a tiny sphere of rock and water, turns to face a celestial heartbeat that has pulsed for 4.5 billion years. We feel its warmth on our skin. We see the world it reveals. We owe our very existence to it. But what is it really? We call it the sun. We see it as a simple, friendly circle in the sky. A source of light, a bringer of summer. But this perception is a profound illusion. The reality of our star is a place of such scale, such power, and such unimaginable violence that it defies our everyday comprehension. It is a cosmic engine, a nuclear furnace, and a gravitational god that holds our entire world, and all the worlds we know, in its unwavering grip. Today, we begin a journey. We are going to strip away the familiar and confront the extraordinary. We will travel across 93 million miles of empty space to visit this celestial titan. We will dive through its layers of superheated gas, down into a core where the very fabric of reality is torn apart and reforged. This isn't just a collection of trivia. This is the biography of a star, our star. And by the end, the friendly circle in the sky will look very, very different. This is part 1 of 100 mind-blowing facts about the sun. Let's begin where we must, with a concept that our brains are simply not built to handle: scale. We live our lives on a human scale, but the sun operates on a cosmic one. When we say the sun is big, the word big loses all meaning. Here is a fact that sets the stage for everything else. The sun accounts for 99.86% of all the mass in our entire solar system. Stop and think about that. Take Jupiter, a planet so vast it could swallow every other planet combined. Take Saturn with its glorious, sprawling rings. Take all the gas giants, all the rocky worlds like our own, every asteroid in the belt, every comet in the Oort cloud, every moon, every speck of dust. Gather it all together. All of that, everything that is not the sun itself, makes up a pathetic, almost laughable 0.14% of the solar system's mass. It is a rounding error. We are living in the sun's solar system. It doesn't just dominate our cosmic neighborhood. For all practical purposes, it is our cosmic neighborhood. To put its size in a more visual way, if you were to imagine the sun as a standard front door, the Earth would be the size of a small coin. Jupiter, the biggest of the planets, would be about the size of a basketball. The sheer volume is even more staggering. You could fit 1.3 million planet Earths inside the sun. Not side by side. You could fill it up like a gumball machine, and you would need 1.3 million Earths to do it. And yet, for all this grandeur, our sun is not a particularly special star. In the grand cosmic scheme, it's actually quite average, maybe even a little on the small side. It's officially classified as a G-type main sequence star, a term astronomers have affectionately nicknamed a yellow dwarf. But even that name is a lie, a trick of the light. The sun isn't actually yellow. This is one of the most fundamental misconceptions we have about it. The sun's light is pure, unfiltered white. It emits light across the entire visible spectrum in almost equal measure. The reason it appears yellow, orange, or red to us is because of our own planet's atmosphere. The Earth's air scatters shorter wavelength light, like blue and violet, more effectively than longer wavelength light, like red and yellow. So when we look at the sun, especially when it's low on the horizon and its light has to travel through more atmosphere to reach us, the blues have been scattered away, leaving the warmer colors behind. If you were floating in space, looking at our star without the filter of our atmosphere, you would see it for what it truly is: a brilliant, dazzlingly white orb. So what is this white-hot giant made of? It isn't made of rock or fire in any way we would understand it. It is an enormous ball of gas, so massive that it has been crushed by its own gravity. The composition is surprisingly simple. About 74% of the sun's mass is hydrogen, the simplest and most abundant element in the universe. About 24% is helium, the second simplest. The remaining couple of percent is a collection of other elements: oxygen, carbon, iron, neon, which astronomers collectively, and rather cheekily, just call metals. This simple recipe of hydrogen and helium is the standard fuel for stars across the universe. The sun is held together by the most powerful force in the cosmos over large scales: gravity. Its own mass is constantly trying to crush it, to pull every single atom towards its center in a relentless, desperate collapse. If gravity were the only force at play, the sun would have imploded in on itself billions of years ago. But it hasn't. It hangs there in a perfect, stable balance. Which means there must be an opposing force, an outward push of unimaginable power, fighting gravity to a perfect standstill. That force is born in the sun's core, and it is the source of all its energy. It is the engine of the stars, nuclear fusion. Deep in the heart of our sun, the conditions are unlike anything in our daily experience. The temperature reaches a staggering 15 million degrees Celsius, or about 27 million degrees Fahrenheit. The pressure is even more extreme, over 250 billion times the atmospheric pressure we feel on Earth's surface. It's a pressure so immense that it's like having the weight of a trillion cities bearing down on a single postage stamp. Under these insane conditions of heat and pressure, the very nature of matter breaks down. There are no solids, no liquids, not even gas as we know it. There is only plasma, a roiling sea of atomic nuclei and free electrons, stripped from each other by the sheer energy of their environment. Here, in this crucible, hydrogen atoms, which are just single protons, are moving at incredible speeds. They are smashing into each other with such violence that they overcome their natural electrical repulsion, the force that normally keeps positively charged protons apart. When they collide with enough force, they fuse together. Through a process called the proton-proton chain reaction, four separate hydrogen protons are gradually fused into a single, heavier helium nucleus. But here is the magical part, the secret that powers the entire universe. If you were to take the mass of the four initial hydrogen protons and compare it to the mass of the final helium nucleus, you would find that the helium nucleus is slightly less massive. About 0.7% of the original mass has simply vanished. It's gone. So where did it go? It was converted directly into pure energy, in accordance with Albert Einstein's most famous equation, E equals mc squared. That equation tells us that energy equals mass times the speed of light squared. Because the speed of light is such an enormous number, and the speed of light squared is an astronomically large number, it means that a tiny amount of mass can be converted into a colossal amount of energy. Every single second, deep in the core of our sun, approximately 600 million tons of hydrogen are being fused into 596 million tons of helium. That missing 4 million tons of matter is what becomes sunlight. Every second, the sun annihilates 4 million tons of itself, converting it into the energy that warms our world, powers photosynthesis, and makes life on Earth possible. This process has been going on for 4.5 billion years, and it will continue for about another 5 billion. The sun has enough fuel in its core to keep this incredible reaction going for an immense stretch of time. So this energy, born from annihilated matter, is released in the form of incredibly high-energy photons called gamma rays. But the journey of one of these photons from the core to the surface is one of the most epic, arduous, and mind-bogglingly long journeys in the solar system. You might think that since the photon is a particle of light, it should zip out of the sun at the speed of light. That is not what happens. The sun's interior is not empty space, it is an incredibly dense plasma. When a gamma-ray photon is born in the core, it travels for only a few millimeters before it slams into another particle. It is absorbed and then re-emitted in a random direction. It travels a few more millimeters and gets absorbed and re-emitted again, and again, and again, for thousands upon thousands of years. This process is called a random walk. The photon is trying to escape, but it is trapped in a cosmic pinball machine, bouncing from particle to particle with no clear path out. The journey that should take just over 2 seconds at the speed of light, from the center of the sun to its surface, instead takes, on average, a staggering 170,000 years. Let that sink in. The sunlight that warmed your face this morning, the light that is hitting your eyes right now, began its life in the core of the sun while Neanderthals still walked the earth. It has been traveling inside the sun, on its long and torturous journey for over 100,000 years. And then, once it finally breaks free from the surface, it takes a mere 8 minutes and 20 seconds to cross the 93 million mile void of space to reach our planet. The contrast between those two journeys, 170,000 years and 8 minutes, tells you more about the sheer density of the sun's interior than almost any other fact. To truly understand this journey, we have to understand the sun's anatomy. Like our planet, the sun has layers, but they are layers of plasma, defined by temperature, density, and how they transport energy. Let's take that journey with our ancient photon, from the inside out. It all begins, as we've discussed, in the core. The core makes up the inner 25% of the sun's radius. It is the only place where the temperature and pressure are high enough for nuclear fusion to occur. It is the sun's engine room, a place of unimaginable extremes. All the energy the sun will ever produce is born right here. It is so dense that a single cubic foot of the core's plasma would weigh over 2 tons. It is the heart of the star, a self-sustaining nuclear reaction of planetary proportions. Surrounding the core is the next layer, the radiative zone. This is a vast, thick shell that extends from the edge of the core out to about 70% of the sun's radius. It is in this zone that our photon endures its 170,000-year imprisonment. Energy here is transported by radiation, which is where the zone gets its name. Photons literally radiate outwards, being absorbed and re-emitted countless trillions of times. The plasma here is still incredibly dense and hot, reaching millions of degrees, but it's not quite hot or dense enough for fusion to occur. It is a passive, incredibly thick blanket, slowly and inefficiently allowing the core's energy to seep outwards. As we move further from the center, the temperature and density of the plasma finally begin to drop. At about 70% of the way out from the center, the process of energy transport changes dramatically. We enter the convective zone. Here, the plasma is no longer dense enough to effectively transport heat by radiation. Instead, it behaves like a giant, boiling pot of water. Huge blobs of hot plasma, heated from the radiative zone below, become buoyant and begin to rise. These are not small bubbles. These are continent-sized convection cells of roiling gas, some measuring thousands of kilometers across. As they rise, they carry their heat towards the surface. Once they reach the top, they release their energy, cool down, become denser, and then sink back down into the sun's interior to get heated up all over again. This constant, violent churning, this celestial boiling, is the dominant way energy is transported through the final 30% of the sun's interior. It is a process of perpetual motion on a scale that is difficult to fathom. This brings us to the part of the sun that we can actually see, its visible surface. But the sun doesn't have a solid surface like Earth. What we perceive as the surface is a layer called the photosphere, which literally means sphere of light. This is the point where the plasma of the sun finally becomes thin enough for our photon, after its 100,000-year journey, to escape into space. The photosphere is surprisingly thin, only about 500 kilometers thick, which is razor-thin compared to the sun's total radius. When we look at the photosphere with a specialized solar telescope, we see that it is not a smooth, uniform surface. It is covered in a seething, granular pattern, like cobblestones or grains of rice. These are called granules, and each one is the top of one of those massive convection cells from the convective zone rising up from below. Each individual granule is about the size of the state of Texas. The bright center is where the hot plasma is rising, and the darker edges are where the cooler plasma is sinking back down. This entire surface is in a constant state of flux. A single granule only lasts for about 8 to 20 minutes before it dissipates and is replaced by another, born from the boiling chaos beneath. The entire surface of the sun is being replaced every few minutes, and it is on this turbulent surface that we see some of the sun's most famous features, sunspots. A sunspot appears dark simply because it is cooler than the surrounding photosphere. But cool is a very relative term here. The surface of the photosphere is about 5,500 degrees Celsius or 9,900 Fahrenheit. A large sunspot might be only 3,500 degrees Celsius. While that is still incredibly hot, hot enough to vaporize any known material. The temperature difference makes it appear as a dark blemish against the brighter, hotter background. Sunspots are not random cold patches. They are areas of intense, concentrated magnetic activity. The sun has a powerful magnetic field, generated by the flow of electrically charged particles in its interior. In some places, this magnetic field becomes twisted and concentrated, and it bursts through the photosphere. These magnetic field lines are so powerful that they inhibit the normal flow of convection from below, effectively blocking the heat from reaching the surface. This is what creates the cooler, darker spot. Many sunspots are enormous, easily large enough to swallow the Earth whole, and some are so big they can be seen from Earth without a telescope, using proper and safe solar filters, of course. They are windows into the sun's powerful and mysterious magnetic engine, an engine that drives the most violent weather in the solar system. As we move outwards from the visible surface, we enter the sun's atmosphere, which is also comprised of several distinct layers. Immediately above the photosphere is a thin, wispy layer called the chromosphere, or sphere of color. It gets its name because during a total solar eclipse, just as the main disk of the sun is blocked out, this layer becomes visible for a few fleeting seconds as a faint, reddish-pink ring. This red glow comes from the strong emission of light from hydrogen atoms at that specific wavelength. The chromosphere is a chaotic and dynamic place. It is covered in gigantic, fiery jets of gas called spicules, which are constantly shooting upwards and collapsing back down. These spicules can be thousands of kilometers long and last only a few minutes, making the chromosphere look like a shaggy, burning carpet. Beyond this lies the final and perhaps most mysterious layer of the sun, the corona. The corona is the sun's vast, ethereal outer atmosphere. It is made of incredibly tenuous plasma that stretches millions of kilometers out into space. Like the chromosphere, it is normally completely invisible, drowned out by the intense glare of the photosphere. But during a total solar eclipse, when the moon perfectly blocks the sun's bright face, the corona reveals itself in all its glory. It is one of the most beautiful and awe-inspiring sights in all of nature, a ghostly, pearly white halo of streamers and loops fanning out into the blackness of space. But the corona holds one of the greatest paradoxes in modern astrophysics. As we've journeyed from the sun's core outwards, the temperature has steadily dropped, from 15 million degrees in the core to a mere 5,500 degrees at the photosphere. Logically, the atmosphere above the surface should be even cooler, but it's not. It's catastrophically, impossibly hotter. The temperature of the corona absolutely skyrockets, reaching between 1 and 2 million degrees Celsius, and sometimes even hotter in specific regions. This is the coronal heating problem, and it is a massive, unsolved mystery. How can the sun's outermost atmosphere be hundreds of times hotter than the visible surface right below it? It defies the normal laws of thermodynamics. It's like walking away from a campfire and suddenly feeling the air get immensely hotter instead of cooler. Scientists have several competing theories. Perhaps it's heated by countless tiny magnetic explosions called nanoflares, or maybe by energy carried upwards by magnetic waves. But as of now, no one knows for sure. The beautiful, ghostly halo we see during an eclipse is a clue to a profound physical puzzle that we are still trying to solve. So far, we have journeyed through a star that is both mind-bogglingly large and incredibly complex. We've seen how it generates its power through the sacrifice of its own mass. We've followed a single particle of light on its ancient journey from the core, and we've uncovered a fundamental mystery at its very edge that continues to baffle the brightest minds on Earth. We have explored the star at rest, in its state of perfect, majestic equilibrium. But the sun is not always at rest. Its magnetic heart is a tangled, dynamic beast. And when that beast awakens, the results are the most powerful and violent events our solar system ever witnesses. The story of the sun is just beginning. In our journey so far, we have explored the sun at rest. We have traveled from its incomprehensible scale down through its layers of plasma, to a core where matter is annihilated to create light, and back out to a mysterious, superheated atmosphere. We have seen the sun as a marvel of physics, held in a perfect, delicate balance between the inward crush of gravity and the outward fury of nuclear fusion. It is a star in equilibrium, a majestic and stable engine. But this stability is an illusion. The sun is not a serene, unchanging lamp. It is a dynamic, magnetic beast with a temper, a heartbeat, and a cycle of violence that governs the entire solar system. The sun is alive with activity, and its moods have profound consequences for us here on Earth. Welcome to part 2. To understand the sun's temper, we must first understand its heart, and I don't mean the nuclear core. I mean its magnetic heart. The sun is a gigantic magnet, but it is not a simple bar magnet like the ones we stick on a refrigerator. Its magnetic field is a complex, chaotic, and ever-changing entity born from the unique way the sun rotates. Unlike a solid planet like Earth, the sun is a ball of plasma, and it doesn't rotate as a single, solid body. This is a crucial concept known as differential rotation. The sun's equator spins much faster than its poles. A point on the solar equator completes a full rotation in about 25 Earth days. But a point near the poles takes a leisurely 35 days to make the same journey. This difference in rotational speed has a staggering effect on the sun's magnetic field. Imagine the magnetic field lines in a quiet state, running neatly from the North Pole to the South Pole, like lines of longitude on a globe. Now, because the equator is moving faster, it drags those field lines along with it. The lines at the equator race ahead, while the lines at the poles lag behind. Over time, these neat lines of longitude get stretched, twisted, and wrapped around the sun, like winding a rubber band tighter and tighter. This process, driven by the sun's differential rotation and the churning of the convective zone, is called the solar dynamo. It is the engine that generates the sun's immense magnetic energy. As these magnetic field lines get more and more tangled, they store a colossal amount of energy. Eventually, these twisted ropes of magnetic force become unstable. They rise through the sun's interior and burst through the photosphere, creating the sunspots we discussed in part 1. Every sunspot is a breach, a place where a powerful, concentrated loop of magnetism has broken through the surface. They always appear in pairs, a north and south magnetic pole, marking where the loop comes out of the sun and where it goes back in. But this is just the beginning. This constant winding and tangling of the magnetic field doesn't happen randomly. It follows a distinct, rhythmic pattern. This brings us to one of the most important discoveries in solar physics: the solar cycle. The sun has a heartbeat that pulses, on average, every 11 years. This is the time it takes for its magnetic activity to go from a period of calm to a period of intense violence, and back to calm again. We track this cycle by counting the number of sunspots on the sun's surface. A cycle begins at what we call the solar minimum. During this time, the sun can be eerily quiet. For days or even weeks on end, its face might be completely blank, with no sunspots at all. Its magnetic field is relatively weak and organized. It is the gentle Sunday. But then things begin to change. A few sunspots start to appear, not at the equator, but at the mid-latitudes, around 30 to 40 degrees north and south. As the cycle progresses over the next several years, the number of sunspots steadily increases. More and more magnetic loops burst through the surface. The sun becomes more and more active. This period of peak activity is known as the solar maximum. The sun's face is now covered in large, complex groups of sunspots. Its magnetic field is a tangled, chaotic mess. The rubber band has been wound as tightly as it can go. This is the angry sun, and it is during this time that the most dramatic and powerful solar events occur. After reaching its peak, the activity begins to decline. The number of sunspots decreases, and the new spots that form appear closer and closer to the equator. Finally, after about 11 years, the sun returns to a state of calm, another solar minimum, and the cycle begins anew. If you were to plot the latitude where sunspots appear over time, you would get a beautiful pattern known as the butterfly diagram, as the wings of the butterfly show the spots emerging at mid-latitudes and migrating towards the equator as each cycle progresses. But the 11-year sunspot cycle is only half the story. Something even more profound happens at the peak of each cycle. The sun's entire magnetic field, its global north and south poles, completely flips. The magnetic North Pole becomes the South Pole, and the South Pole becomes the North. Then, 11 years later, at the next solar maximum, it flips back again. So, for the sun's magnetic field to go through a full cycle, returning to its original state, it actually takes 2 sunspot cycles, or 22 years. This is known as the Hale cycle. Our star literally reboots its entire magnetic personality every decade. And this cycle is not perfectly regular. Some cycles are much more intense than others, and sometimes the cycle can almost disappear entirely. Between the years 1645 and 1715, sunspot activity virtually ceased. Astronomers of the time were baffled. This period, known as the Maunder Minimum, coincided with the coldest part of a climatic period on Earth called the Little Ice Age. While the exact link is still debated, it is a powerful reminder that even the sun's quiet moods can have a dramatic influence on our world. So what happens when the sun is at its angriest, at the peak of the solar maximum, when its magnetic field is a tangled, high-tension mess? The stored energy has to be released. And when it is, it happens in the form of the largest explosions in our solar system. The first of these events are called solar flares. A solar flare is an intense, localized eruption of high-energy radiation from the sun's surface. Think of it as the flash from that snapping rubber band. When the tangled magnetic field lines above a sunspot group suddenly reconfigure into a simpler, lower-energy state, the excess magnetic energy is instantly converted into a blinding burst of radiation across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. The amount of energy released in a large solar flare is staggering. A major flare can unleash the energy equivalent of millions of 100-megaton hydrogen bombs, all exploding at once. This isn't a slow burn, it's an instantaneous flash. Flares are classified by their X-ray brightness on a lettered scale. C-class flares are common and relatively weak. M-class flares are medium-sized and can cause brief radio blackouts on Earth. And then there are the X-class flares. X-class flares are the monsters. They are the major events, and the scale is logarithmic, meaning an X2 flare is twice as powerful as an X1, but an M1 is 10 times more powerful than a C1. The most powerful flare ever recorded, in 2003, was so powerful it overloaded the sensors on our solar-observing satellites. They cut out at X28, but the flare may have been as powerful as an X45. Because a solar flare is an explosion of electromagnetic radiation, its effects travel at the speed of light. That means it takes only 8 minutes and 20 seconds for the danger to reach us. The first thing to arrive is the blast of X-rays and ultraviolet radiation. This radiation slams into the upper part of Earth's atmosphere, the ionosphere. This sudden dose of energy ionizes the atoms there, causing the ionosphere to become dense and absorptive. This can cause immediate and widespread high-frequency radio blackouts on the sunlit side of the Earth. GPS signals can also be disrupted, as they have to pass through this turbulent layer. For a few minutes to a few hours, long-distance communication and navigation can simply cease to function. But flares are often just the opening act. Sometimes, the same magnetic explosion that creates the flare also causes a much larger, more significant event. It causes the eruption of a colossal bubble of solar material into space. This is a coronal mass ejection, or CME. While a flare is a flash of light, a CME is a blast of stuff. It is a cloud of over 1 billion tons of plasma, protons and electrons, and the tangled magnetic field that contains it, all hurled out from the sun at incredible speeds, sometimes exceeding millions of miles per hour. Imagine a cannonball of gas, wider than the sun itself, screaming across the solar system. That is a CME. Not all flares have CMEs, and not all CMEs have flares, but the most powerful events often involve both. And unlike the flare's radiation, which reaches us in 8 minutes, the CME cloud travels much more slowly. It can take anywhere from 1 to 4 days for this plasma storm to cross the 93 million miles to Earth. This delay is both a blessing and a curse. It gives us time to prepare, but it also means that after we see a major flare, we may have to watch and wait, for days, for the potential impact of an Earth-directed CME. So what happens when one of these billion-ton clouds of magnetized plasma strikes our planet? Fortunately, the Earth is not defenseless. We are protected by a planetary superhero, our magnetic field, the magnetosphere. Generated by the molten iron core of our planet, the magnetosphere extends tens of thousands of miles out into space, forming an invisible shield. Most of the time, it deflects the constant stream of particles from the sun, known as the solar wind. But a CME is not the solar wind. It is a tidal wave. When a CME slams into our magnetosphere, it's a cosmic collision. The shield is compressed, deformed, and squeezed. A huge amount of energy from the CME is transferred into our planet's magnetic environment. This massive disturbance is called a geomagnetic storm, and it has two very different consequences, one of breathtaking beauty and one of potentially catastrophic danger. The beauty is the aurora. During a geomagnetic storm, some of the high-energy particles from the CME are funneled along the Earth's magnetic field lines down towards the North and South Poles. As these particles rain down into our upper atmosphere, they collide with atoms of oxygen and nitrogen. These collisions excite the atoms, and when the atoms return to their normal state, they release that excess energy as photons of light. The color depends on the atom. Oxygen at high altitudes glows a beautiful, ethereal green, the most common color of the aurora. Oxygen at even higher altitudes can glow red. Nitrogen atoms produce stunning hues of blue and deep violet. The shimmering, dancing curtains of the aurora borealis and australis are the visible signs of our atmosphere being bombarded by a storm from the sun. During a powerful geomagnetic storm, these displays can be seen far from the poles, sometimes visible in places like Florida or Texas. But the danger is just as real. The same storm that paints the sky with light can wreak havoc on our modern technological civilization. The flood of high-energy particles can damage the sensitive electronics of satellites in orbit. They can increase the atmospheric drag on satellites in low Earth orbit, causing their orbits to decay. During a major storm, satellite operators may have to shut down non-essential components to protect them. GPS accuracy can be reduced from meters to miles. Astronauts on the International Space Station are also at risk. They are above much of the Earth's protective atmosphere, and during a severe storm, they have to take shelter in the most heavily shielded parts of the station to protect themselves from dangerous levels of radiation. This radiation risk is one of the single biggest challenges for any future long-duration human mission to the Moon or Mars, which would take astronauts completely outside the protection of Earth's magnetosphere. However, the greatest threat from a geomagnetic storm lies not in space, but right here on the ground. When the Earth's magnetic field is rapidly shaken and deformed by a CME, it induces electrical currents in the ground beneath our feet. These are called geomagnetically induced currents, or GICs. These currents seek out the path of least resistance, and in our modern world, that means long conductors, like oil and gas pipelines, railway lines, and most critically, high-voltage power transmission lines. These rogue DC currents can flow into our power grids, which are designed for AC power. They can overload and overheat the giant transformers at electrical substations, the critical nodes of the entire power system. If these transformers are damaged or destroyed, they can cause widespread, cascading blackouts. And these are not just any pieces of equipment. A large, high-voltage transformer can weigh hundreds of tons, cost millions of dollars, and take months or even years to build and replace. A severe geomagnetic storm could, in theory, damage hundreds of these transformers across a continent simultaneously. This is not a theoretical threat. It has happened before. In March 1989, a powerful CME struck Earth, triggering a geomagnetic storm that collapsed the entire power grid of Quebec, Canada, in less than 90 seconds. 6 million people were plunged into a blackout that lasted for 12 hours. The storm was so intense that auroras were seen as far south as Cuba. But even the 1989 event pales in comparison to the historical benchmark, the great-great-grandfather of all solar storms, the Carrington event. In September 1859, a British astronomer named Richard Carrington was in his observatory sketching a large group of sunspots when he witnessed an intensely brilliant flash of white light erupt from them. It was the first ever observation of a solar flare. What he didn't know was that this flare was associated with a monstrous CME hurled directly at Earth at incredible speed. It crossed the distance from the Sun to Earth in just 17.6 hours, a journey that normally takes 3 days. The resulting geomagnetic storm was the most powerful in recorded history. The technology of 1859 was the telegraph. The induced currents in the telegraph lines were so strong that operators were getting electric shocks. Telegraph paper spontaneously caught fire. Some operators found that they could disconnect their batteries and continue sending messages using only the auroral current induced in the wires by the storm. The auroras were the most spectacular part. They were so bright that people in the northeastern United States could read a newspaper by their light at midnight. They were seen all over the world, in the Caribbean, in Mexico, in Hawaii. The Carrington event was a fascinating historical curiosity. But now, ask yourself a terrifying question. What if a storm of that magnitude were to happen today? In our world that is completely dependent on electricity and space-based technology, a modern Carrington event could be an unprecedented catastrophe. It could lead to the collapse of power grids on a continental scale, blackouts that could last not for hours or days, but for weeks, months, or even years as we struggle to replace hundreds of destroyed transformers. Without electricity, the world would grind to a halt. No clean water being pumped to our homes. No refrigeration for food or medicine. No gas stations. No banking, no communications, no internet. It would be a disaster on a global scale with a potential economic cost measured in the trillions of dollars. It is, according to many government agencies, one of the most severe but least appreciated natural disaster threats facing the modern world. The sun, our life-giving star, the source of all our energy and warmth, is also the source of the single greatest natural threat to our way of life. It is a constant reminder that we live in a cosmic shooting gallery, and our connection to the universe is far more direct and far more dangerous than we often like to admit. We have now seen the sun's magnetic fury. We have seen how its 11-year mood swings can paint our skies with light and threaten to send our civilization back to the Dark Ages. But the sun's influence doesn't end with these explosive, intermittent storms. There is a constant, unending stream of material flowing from the sun, a stellar wind that carves out a vast bubble of influence in interstellar space and touches every planet in our solar system, including our own. The story of the sun's steady, relentless breath and its ultimate, spectacular fate is yet to come. In Part 3, we will explore the solar wind, the heliosphere, the strange particles called neutrinos that stream through our bodies every second, and we will journey billions of years into the future to witness the final, dramatic death of our star, an event that will consume the inner planets and reshape the solar system forever. The most epic chapter of the sun's biography is still waiting to be told. We have journeyed into the heart of a star, witnessing a furnace that forges light from matter. We have watched that star awaken, its magnetic fury unleashing the most powerful explosions in the solar system, storms of plasma that can both paint our skies with impossible beauty and threaten the foundations of our civilization. We have seen the sun in its moments of violence. But its influence is far more constant, more pervasive, than these intermittent outbursts suggest. The sun does not just occasionally shout at the solar system. It perpetually breathes. This stellar exhalation travels billions of miles in every direction, creating a unique environment, a bubble of solar influence that we call home. And to understand our place in the galaxy, we must first understand this breath. Welcome to part 3. This constant outflow of material from the sun is known as the solar wind. It is not a wind in the sense of moving air. It is a tenuous, unending stream of charged particles, mostly protons and electrons, that are constantly escaping from the sun's corona and flowing outwards through space. Remember the coronal heating problem from part 1? The mystery of why the sun's outer atmosphere is millions of degrees hotter than its surface? That extreme heat is what gives these particles enough energy to escape the sun's immense gravitational pull. They are effectively boiled off the top of the solar atmosphere, accelerated to supersonic speeds. The solar wind is not a gentle breeze. Near Earth, it travels at an average speed of about 400 kilometers per second, which is roughly 1 million miles per hour. That's fast enough to travel from Los Angeles to New York in about 20 seconds. And it isn't uniform. There are 2 types of solar wind. There is a slow wind, which flows from the sun's equatorial regions, and a fast wind, which can travel at twice the speed, gushing from openings in the sun's magnetic field over the poles, known as coronal holes. As the sun rotates, these streams of fast and slow winds spiral outwards through the solar system, like water from a spinning sprinkler, creating complex, interacting shockwaves and turbulent structures in space. This solar wind fills the entire solar system. It is the reason that comet tails always point away from the sun, regardless of which direction the comet is traveling. The comet's icy nucleus is vaporized by sunlight, and the solar wind acts like a cosmic hairdryer, pushing that gas and dust out into a long, glowing tail. Every planet, every moon, every asteroid is constantly bathed in this stream of high-energy particles. Planets with strong magnetic fields, like Earth and Jupiter, are protected, their magnetospheres carving out a cavity of safety in the wind. But worlds without that protection, like Mars and our own moon, have their surfaces directly exposed to this constant particle bombardment, a process that has slowly stripped away Mars's ancient atmosphere over billions of years. The solar wind travels incredibly far, but it does not travel forever. Eventually, far beyond the orbit of Pluto, it begins to encounter a new environment, the interstellar medium. This is the thin gas and dust that drifts in the vast, empty spaces between the stars. The solar wind pushes against this medium, blowing a gigantic bubble in it. This bubble is called the heliosphere, and it is the true extent of the sun's domain. It is the region of space dominated by the sun's magnetic field and its outflow of particles. Our entire solar system, all the planets, and everything we have ever known, exists deep inside this protective cosmic cocoon. The boundary where the solar wind, after traveling for billions of miles, finally slows down to subsonic speeds is called the termination shock. Humanity has actually crossed this boundary. The Voyager 1 and Voyager 2 spacecraft, launched in 1977, have been traveling for over 4 decades. In 2004, Voyager 1, then nearly 9 billion miles from home, sent back data showing it had crossed this invisible frontier. Voyager 2 followed in 2007. They had entered the final region of the heliosphere, a turbulent area called the heliosheath. Then, in 2012, came an even more momentous milestone. Voyager 1 crossed the ultimate boundary, the heliopause. This is the edge of the bubble, the point where the pressure of the solar wind is no longer strong enough to push back the interstellar medium. It left the solar system. For the first time, a human-made object had entered interstellar space. It is now swimming in the cosmic sea between the stars, a silent ambassador from a world that turns around a yellow dwarf star. It is a testament to the sheer scale of the sun's influence that it took a spacecraft traveling at over 38,000 miles per hour more than 35 years just to reach the edge of its breath. But the sun sends out more than just light and charged particles. Its nuclear core is a factory for one of the most bizarre and ghostly particles in the entire universe, the neutrino. Neutrinos are a byproduct of the nuclear fusion process. For every helium nucleus created in the sun's core, 2 neutrinos are born, and they are unlike any other particle we've discussed. They have almost no mass, no electrical charge, and they interact so weakly with other matter that they are almost undetectable. They are ghosts. While a photon of light takes 170,000 years to escape the sun's dense interior, a neutrino makes the same journey in just over 2 seconds. It doesn't bounce off anything. It doesn't get absorbed. The incredibly dense plasma of the sun's core is as transparent as empty space to a neutrino. It zips out of the core, through the sun, and into space at nearly the speed of light. And they are produced in unimaginable numbers. Every single second, about 65 billion solar neutrinos pass through every square centimeter of your body, even at night when the sun is on the other side of the planet, because the entire Earth is also completely transparent to them. They stream through you, through the planet, and out the other side without leaving a trace. For decades, this created a profound mystery called the solar neutrino problem. Our theories of nuclear fusion predicted a certain number of neutrinos should be streaming from the sun. But when we finally built massive, sensitive detectors deep underground to try and catch them, we only found about a third of the number we expected. Was our understanding of the sun's core wrong? Or was something wrong with our understanding of physics? The answer, it turned out, was the latter. Scientists discovered that neutrinos can change flavor. There are 3 types: electron, muon, and tau neutrinos. The sun only produces electron neutrinos, but on their journey to Earth, they can oscillate or change into the other 2 flavors, which our early detectors weren't designed to see. The discovery of neutrino oscillation was a monumental breakthrough in particle physics, and it was a puzzle that was solved by studying the ghostly emissions from the heart of our sun. So we have a star that breathes a wind, creates a bubble of influence, and showers us in ghost particles. But what about the sun itself? What is its future? Like all living things, stars are born, they live, and they die. Our sun is currently in its middle age. It is about 4.6 billion years old, and it is in the most stable and long-lasting phase of its life, the main sequence, where it happily fuses hydrogen into helium in its core. It has enough hydrogen fuel in its core to continue this process for another 5 billion years or so. For all of human history, and for billions of years to come, the sun will remain largely as it is today. But eventually, the fuel will begin to run out. In about 5 billion years, the hydrogen in the sun's core will be exhausted. Fusion will cease. And at that moment, the delicate balance that has defined the sun for 10 billion years will be broken. Gravity will win. The core, no longer supported by the outward pressure of fusion, will begin to collapse in on itself. As it collapses, the pressure and temperature will skyrocket. This will heat up a shell of hydrogen surrounding the now inert helium core. The temperature in this shell will become so high that hydrogen fusion will ignite there instead. This is the beginning of the end. This new shell-burning phase will be ferociously intense, producing far more energy than the core-burning phase did. This massive new outward pressure will cause the sun's outer layers to expand dramatically. The sun will begin to swell. It will grow larger, and as its surface expands, it will cool down, turning from a brilliant white to a deep, menacing red. The sun will leave the main sequence and become a red giant. And it will be enormous. It will swell so large that it will first consume Mercury, its closest planet, vaporizing it instantly. Then it will continue to expand, swallowing Venus. Its searing outer atmosphere may even expand far enough to engulf the Earth. Our planet will either be consumed entirely, or its orbit will be pushed outwards, leaving it a charred, molten, lifeless cinder, orbiting just outside the star that once gave it life. All the oceans will have boiled away long before this, and the atmosphere will have been stripped into space. The final fate of Earth is a matter of some debate, but one thing is certain: our world will not survive the sun's old age. The Sun will remain in this red giant phase for about 1 billion years. During this time, the collapsing core will eventually become so hot and dense, reaching about 100 million degrees Celsius, that a new type of fusion will ignite. The helium ash that has been building up for billions of years will itself begin to fuse, creating heavier elements like carbon and oxygen. This is called the helium flash, a brief but violent event that will restabilize the Sun for a time. But the helium fuel will burn much, much faster than the hydrogen did. After only about 100 million years, the helium in the core will also be exhausted. The Sun is not massive enough to fuse carbon and oxygen into even heavier elements. So once the helium is gone, fusion in the core will cease for good. The star will enter its final death throes. It will shed its outer layers in a series of dramatic thermal pulses, puffing them out into space. This will create one of the most beautiful objects in the cosmos, a planetary nebula. This has nothing to do with planets. It's an old, mistaken name. It is a vast, intricate, glowing cloud of gas, the Sun's former atmosphere, illuminated by the tiny, intensely hot core left behind. For a few tens of thousands of years, this beautiful celestial ghost will be the Sun's final, spectacular monument. And what will be left at the center of this nebula? The Sun's collapsed core. An object about the size of the Earth, but containing about half the Sun's original mass. An object of incredible density, where a single teaspoon of its material would weigh several tons. This is a white dwarf. It is no longer generating any new energy. It is simply a stellar ember, the hot, leftover core of a once mighty star. And for the rest of time, over trillions upon trillions of years, a timescale far longer than the current age of the universe, this white dwarf will simply cool down, fading slowly from brilliant white to yellow to red until it eventually becomes a cold, dark, dead lump of carbon and oxygen, a black dwarf drifting silently in the eternal darkness. That is the ultimate fate of our Sun. A journey from a brilliant white star to a bloated red giant to a beautiful, fleeting nebula and finally to a cold, dark grave. It is a story of cosmic birth, life, and death, played out on a scale of billions of years. From the 99.86% of the solar system's mass it contains, to the 1.3 million Earths that could fit inside it. From the brilliant white light it truly emits, to the 4 million tons of its own mass it annihilates every second. From the 170,000-year journey of a single photon, to the 11-year cycle of its magnetic heart. From the solar flares that explode with the force of 1 million bombs, to the ghostly neutrinos that pass through our bodies every second. From the solar wind that carves a bubble of safety around us in the galaxy, to the red giant it will one day become, consuming its own children. The Sun is not just a light in our sky. It is the anchor of our world, the engine of life, a source of profound mystery, and a constant, humbling reminder of the immense and violent beauty of the universe. It connects us to the grand cosmic story, a story written in the language of gravity, light, and time. And every time we feel its warmth on our face, we are feeling the energy from a process that began before humanity existed, a process that will ultimately end our world, and a process that makes our brief, precious existence possible. The story of the Sun, in the end, is our story.